Okay, we're going to end up by talking about torque, and it's going to lead to MRI. And this is tough, so pay attention, all right? Or make sure you're awake, or go eat something, or whatever. Okay, so here is our equation, right? This is the equation we just figured out. And this is going to be our magic equation, right? So the torque equals mu b sine theta. Okay? All right. So if released from rest, the current loop will do what? So what you're thinking of is this. So you're thinking of, so there's a B field this way, right? And what we want is the wire to be the plane of the wire. So the plane of the wire is perpendicular to the plane of the B field. Okay? So that's what they mean by theta is 0, right? All right, because remember, what's this mu b? Remember, mu b, let's see. Stop. Mu b is points normal, right, to the plane of this. Okay? Let me show you. Hold on. Yeah, right? So here's a circle. Mu b is perpendicular to the plane of the circle. Doesn't really show it really well. Forget it. I guess just that shows it best. Okay? All right. So see, here's two vectors, right? Here's mu b, and then here's b. So the angle between them, maybe we should write it like this. Okay? So this angle is the angle between the mu b and the b. All right. So you have this thing here. You let it go. And what's going to happen? So just use this equation and figure it out. So pause your video and figure it out, please. Well, what's the sign of 0? 0. So what's the torque? 0. All right? All right? Okay. All right. So what we're saying is, you know, if you have a current loop, it doesn't want to be like this. It doesn't want to be like that. It wants to be like this, right? Because if it's like this, it's an equilibrium. The torque is equal to 0. So this is the preferred direction where mu b is parallel to b, where theta is 0 degrees, right? So this is where it wants to be, right? It wants to be in equilibrium where the torque is 0. Okay? So that's what we just said, right? So nothing's going to happen, right? It's not going to flip around. It's where it wants to be, you know? No torque, right? No torque at all. Okay, so now let's just move it a little. Okay, now let's rotate it a little bit, right? So again, this is preferred, but now we're going to rotate it just a little bit. Okay, a lot. Well, I don't know, whatever. All right, we're going to rotate it. In other words, it's not like this anymore. It's like that, okay? Now remember, it wants to be like this, right? Well, it's not, okay? So what's going to happen? So use your equations, and you know theta is less than 90 degrees, and so figure it out, okay? Figure it out. And you have all sorts of good equations you can use, right? I mean, if you don't want to use this one, you can use this one. Okay, what's going to happen? Remember, it wants to be like this. So what's it going to? It's going to be a torque on it, right? The torque is going to want this thing to go like that, right? Right? Okay. Okay, so okay. I mean, let's figure it out with this. Okay, let's figure it out with this. So what's the direction of the current right here? It's out, right? So IL is this way, B is that way. So what's the force? You know? Okay? So you can use either one of these equations, but I think the easiest is just to do this. Here's no torque because it's in the preferred direction. Here we spun it a little bit, we rotate it a little bit. So we want to go back to that preferred direction, right? So it's going to be like that. Okay? So it's going to rotate clockwise. Yeah? Because you want that to be in the same direction as that. So it's going to rotate clockwise. All right, now, not yet. Okay, now, here's the question though. So we started off like this, and this is preferred. Now, so is it going to keep going like that? Remember, it wants to be like that. So right now it's like this, sort of, and then there's going to be a torque on it. Now, is it going to keep going? No, because it wants to be like this. Agree? So what do you call that? We learned about this in 105. This is called, so it wants to be like this. It's like that, so it's going to go like that, and it's just going to eventually just end up like that. So that's called stable equilibrium. So here's a fishbowl. Here's something at the bottom. We just give it a little flick. It's going to go like back and forth, back and forth, back and forth, right? Right? It's not going to go out of the bowl, It's just going to go back and forth, back and forth. All right? On the other hand, let's do something really, okay, now let's look at this one. Remember, we want this to be lined up with this. Well, here it's anti-parallel. Well, wait a second, though. Well, you figured it out. I almost gave it away. So look at this formula, look at the angle, and figure it out. Okay, what's the sine of 180? 0. So what's the torque? 0. So what's going to happen? Nothing. All right? Nothing. Nothing's going to happen. But now, remember, we want this and this to have the same direction. So this is way off, right? So now let's rotate this thing just a little, or maybe a lot, I don't know. Let's rotate it. Okay, let's rotate it. Okay? So now we just rotate it a little bit this way. Remember, where does it want to be? It wants that to be in the same direction as, it wants that to be in the same direction as that. So what's it going to do? Well, you figured out. Okay? Use your formula. So pause your video and figure it out. Okay, if we want this to line up with this, how does it have to rotate? Counterclockwise, right? It has to go like this. Right? That's what it has to do. Okay? Now, here's the question. All right? So it's going to rotate, big time. Right? Now, what's it going to do then? What's it going to do then? Is it going to go back? Is it going to go back to this? No way. It's not going to go back to that. No way it's going to go back to that. And so, yeah. So what do we call that? We call that unstable equilibrium. In other words, here's a fishbowl upside down. You put the thing on top, you give it a little flick, it's down, right? It's never going to come back up again, right? So it's never going to go back. It's never going to go back to that original situation. It's going to go flip, and it's going to kind of hang around there, It's not going to go back to its initial situation. Okay, now here's a silly question for you, really. Which state has the higher energy, the stable state or the unstable state? Think of a mousetrap or something like that. So which state is going to have the highest energy, the stable state or the unstable state? Now the mousetrap, which is, I don't know if it's the best analogy or not, but what does a mousetrap normally do? It's not activated, right? I'm calling that the stable state. If you activate a mousetrap, I'm calling that the unstable state. Because as soon as that mouse touches it, bang, it's back to the stable state, right? It's not going to automatically by itself go to the activated state. So which state has the highest energy? the stable or the unstable, the mousetrap that's not activated or the mousetrap that's activated. I think you have to agree, you know, the unactivated mousetrap is just sitting there, right, just happy. You know, you have to exert some work to activate that spring, right, to set the trap. So the unstable state has the larger energy, okay? And, all right, just like, oops, didn't see that. Okay, so let me go back. Sorry. Okay, so this is where it wants to be, right? This is like the couch potato state, you know, and that's the lowest energy. That has a higher energy because it's not where it wants to be. That has a higher energy because it's not where it wants to be. That has a higher energy because it's not where it wants to be. Okay? All right, so what is that got to do with anything? Okay, so what is that? That's an MRI of somebody's head, right? And here with MRI, what happens in an MRI machine is that magnetic fields are used to flip a proton. What do you mean by that? A proton has a magnetic moment, all right? A proton has a magnetic moment, you know, either up or down. And you can use a magnet, an external magnet, to flip the proton's magnetic moment. When you flip it from a high state to a low state, you got to get rid of that energy somehow. So what happens is a photon is produced, light. And people have figured out how to do that in the brain or in the body. You know, the body has all sorts of protons in it, right? And every proton has a magnetic moment, right? So it's either, you know, let's just say it has an orientation this way or this way, you know. And so they use these external magnets in the MRI, and they flip from, let's just say, a high state to a low state. A photon, light, is emitted, and they can use that light to form these amazing images. Okay? So MRI is an application of what? Magnetism, you know? It's incredible, right? Incredible. Okay, so let's review. So we talked about basic magnetic phenomena, a north pole and a south pole. Like poles repel, unlike poles attract. You can't split a magnet to get a magnetic monopole, as far as we know, but people are still looking for it. A dipole model of magnetism means you have a north and a south. You can get that from a permanent magnet or just by putting a current in a wire, a circular wire loop. Okay, we saw the formulas for the B field for wires and loops and solenoids. Studied the motion of charged particles in magnetic fields. And remember, that means the magnitude and the direction, right? Forces and torques, magnitude and direction. And we skipped this, sorry. Okay, let's quickly review. When you're only going to get a magnetic field when you have a moving charged object, like a current, right? And you have these weird magnetic field lines perpendicular to the wire, you know? And you can figure out the direction with that right-hand rule. Current goes this way, you grab it with the right hand, and the B field lines follow your fingers. That's the basic unit of magnetism. There's no such thing as a magnetic monopole. There's not a north or just a south. It's a dipole. The field lines go away from the north into the south. You can create a bar magnet or a magnetic dipole, like I just said this a couple minutes ago or a minute ago, with a circular piece of wire, right, with a current. Just use your right-hand rule. You can see it's exactly the same, Okay, so we did the wire, the coil, the solenoid. When I say coil, I mean at the center of the coil, right? And you can see that there's a pattern. The B field, mu naught Ni over some length. Or if you just want to say the B field is proportional to current. Larger the current, larger the B field. Okay, this is the first. Here's the magnetic force law. This is the magnitude. That's the direction. And I write these parentheses on purpose so you remember that the alpha is the angle between this and this. And don't forget, you have to know how to do this. So again, if you don't understand it, contact me or the tutor. And okay, since the force is perpendicular to the velocity, the force cannot change the speed of the object. All it can do is change the direction. And you see that at CERN, at the LHC, all the magnets do is make the protons go in a circle. The magnets do not make the protons go faster or slower. The electric field is used to make them go faster. And this was a special case where the velocity is perpendicular to the magnetic field. In that case, the force points towards the center of a circle, so the particle will go in a circle. All right, and you're going to see that in lab. Now this was an external B field, right? We didn't talk about who created it or whatnot. We don't care. But now, this was the same thing, external B field. So external B field, what does it do to a wire? Well, it depends on the direction of the current. We came up with this force law. And that force law, that force law, so that's the magnitude, that's the direction. This is the important example, right, where the wire loop is in the same plane as the magnetic field. And we saw that the force here is that way, the force here is that way, no force here, no force there. So the thing rotates, which is the basis for the electric motor. So we figured out the torque, good review, Physics 105, and we did all that stuff too. Again, good old Physics 105. And that's it. Thank you very much.